Okay, I've just started the recording. Some practical announcements at the beginning of the lecture. First, I guess you have seen the information about the second milestone on the project. So for the second milestone, you need to work on your related work. So some of you have already done this for last week, for last time, last week. And you need maybe to expand a bit and also to write about this in your project journal. And now also to have a presentation like highlighting some of the most important elements in the related work. And also to have a preliminary description of your next work, like at least for the first milestone on what you're going to implement to have a solution with technologies and I don't know, ML models and everything you're going to use, maybe validation, how you're going to if you on what data sets you will validate your results and so on. So this is related to the project, and I've already seen that there are some assignments chosen by you. So you have information about the SSL assignment, about the machine learning assignment. As I've told you, you need to work for a competition on Kaggle for two reasons. The first one is for you to join Kaggle and to see it as a valuable resource. As an ML engineer, and second, in order to work on a practical data set which is not related to research. Like these data sets are provided by companies, they are more practical, and like they are not only like research related data sets. But of course, there is some research into solving this task, and you also have like other machine learning engineers and data scientists who talk about their solutions on Kaggle. You can also find some existing solutions shared as notebooks, and yeah, you can use these resources. Of course, if you use an existing notebook, we expect for you to provide some changes and to be very explicit on the notebook and like the starting notebook and the changes. And you have several suggestions from us. If you really want to work on another competition, you can write me a message. But otherwise, I think you have some pretty interesting topics selected by me in computer vision and in NLP, and some MISC topics on the different types of data, like sales forecasting, stock market prediction from Jane Street, house prices prediction, and like tabular data prediction with fantasy data, not from Titanic, but from something like similar generated with a GAN model called Syntanic, because it was also a competition with Titanic about predicting who survived and who didn't, but people cheated by looking on the correct answers, if you want, because you already know, like for real people, and this is a synthetic data set. So you can choose in the next week your topic. We allow only 10 students per topic, just in order to have some variety. But looking on the first 5 or 6 topics that you have chosen, they are completely different. So there is, I think there aren't any 2 people working on the same topic. Or yeah, we have contradictory. My dear Watson is the current most popular Kaggle competition. Cool. So these were the practical announcements. If you have any questions, is everything okay? I've also uploaded the slides for the lectures, including today's lecture. So I guess that from an organizational point of view, we should have everything on track. The last announcement: if you are really passionate about machine learning, try to apply to the Eastern European Machine Learning Summer School. Like there are some great people presenting there, and you're gonna have like really cool labs. I'm sure they're going to be very useful for you for the next semester when you're going to work on neural networks. Like if you will go through EML, I'm sure you won't have any problems for the neural networks class. Mostly because EML is talking mainly about neural networks. Cool. Otherwise, let's go into today's class. So today's class is going to be a little bit shorter. It's on kernel methods, and it's an intro like to support vector machines, the class for next week. So in the previous chapters, we have looked on linear models for regression and for classifications. And you have seen like our objective was to learn a function y of x and w. And yeah, actually, let me just. Let me just open the PowerPoint because I'd like to write on it. Because a PDF, and on PDFs I cannot write. Cool. So our objective was to learn the function y of x and w, and in doing so, we from the training data we learned the parameters of these models like w. In two ways, like using maximum likelihood. When we are using maximum likelihood, we learn a point estimate, because this is what maximum likelihood does. It computes the most probable, W maximum likelihood, or as a posterior distribution if we use a Bayesian treatment. So in Bayesian treatment, we had a W as a posterior distribution given the training set, and of course we could have computed as a point estimate the maximum a posteriori. But after training, actually the training data is discarded, and you can make the predictions only using these models that we have learned, like using the parameters. And the same approach is also used for non-linear models, such as neural networks. Even there, like you have the training data, you learn the weights, and after you learn the weights, you can just get rid of the training data and make predictions for new data points. Maybe the training data might be useful if you would like to have explainability. Like if your model would have said, I'm classifying this image as a cat because I have seen like these similar images which look like cats. Like in explainability, maybe this training data would have been useful, but in making predictions, the training data is not useful. Like once you know the weights or the parameters of the model, you can just get rid of the training data. But there is a different approach in machine learning, is to keep the training data, or at least part of it, and to use this data to decide which is a value or the class for a new data point. Probably have discussed the data mining as a data mining class of nearest neighbor methods like k-nearest neighbors and other similar approaches. And these are also called memory-based approaches, where you need to compute like the similarity between the data point for which you need to make the prediction and some of the data points in your training set. Like you need to find the most similar items in your training set as compared to the new one, and you're going to make the prediction based on these new items. Like k-nearest neighbor says the majority will decide, the majority of the k elements will decide the class, if it's a classification problem of the data point, and if it's a regression, maybe is the average or some other like a weighted average by taking into account the similarity. These models are sometimes pretty powerful, and I remember that the first time the visual question answering data set and task appeared a couple of years ago, people were just rushing into neural models and using like VGG and ResNet and everything, and trying to make them better and better by adding attention. And there was a very good paper published, which was like a not so naive baseline for visual question answering. And they were using a binning way of putting in bins and then using some k-nearest neighbor similarity for images and for text. Very basic without neural networks. And actually the results were better than the best solution using neural networks and lots of GPUs. Of course, it was at that point. At this point, that method is not so good. But sometimes these methods can be very good, especially as you need a similarity. And if the similarity is computed by a good model, then you can have very good results. These methods, like the memory-based approaches, they are very fast to train. Most of the time, you don't need to do anything, or you need to do some binning or something very simpler. But they are quite slow to make predictions for new data. Like imagine, for k-nearest neighbors, you need to pick the best k items from the training set, the most similar k items. And if you have a large training set, like you need to go through all it's like theta of number of points in the training set. When you think about the complexity, multiplied with the complexity of computing the similarity between two data points. So slower to make predictions, faster to train is not a good thing that they are slow at making predictions, because most of the time, so you need like to have fast inference time or fast prediction time, and not the other way around. And like this is where kernels kick in. And you remember like 2 weeks ago when we talked about linear models for regression, we stopped and said, you remember that the linear model for regression using maximum a posteriori treatment could have been expressed into something called equivalent kernel. So, and actually, most linear parametric models can be recast into this equivalent dual representation. So the kernel representation is also called the dual representation for the model. And in that example, like the prediction for a new point was actually a linear combination of kernel functions evaluated on the training points in the data. Like if you want to predict for a new point x, y of x, it was a linear combination. It was something like a sum from I going from 1 to n, the number of points in the training set, out of ai, so some weights multiplied with a kernel between x and xi. So how similar the new point x is with each point in the training set. And this is called like the dual representation or the kernel representation, which explicitly makes use of these kernel functions. And what is a kernel function? Actually, a kernel function is a dot product in a given space. So this is what we say here. So a kernel function between 2 points, it's actually a dot product, yeah. So it's a dot product between the features in a given space, in a given space mapping or feature space mapping of the 2 points. And this could be like nonlinear function. Like, of course, the dot product is linear, like it's a linear combination. You have the first feature multiplied with the second feature. But these feature mappings, this could be nonlinear. Cool. More on kernel functions, like these functions, they are symmetric, like k of x and x prime, it's the same as k of x prime and x. And their story is pretty interesting, and it kind of follows what happened in machine learning. So they were introduced in the 60s, neglected for many years, and then about 30 years ago, they were reintroduced in machine learning and seen how powerful they are when support vector machines were like the most powerful method. So in the 90s and for about 15 years or close to 20, years, about 10 years ago, when deep learning kicked in, support vector machines were the way to do machine learning. Like if you were a machine learning engineer, you would have used a lot of support vector machines methods, and maybe like online learning or approximate learning for these methods and for support vector machines, and then hyperparameter tuning for them. You have used libs SVM and so on. It was a little bit simpler, yeah, because like you cannot do as much thing with support vector machines as you can do with neural networks nowadays. But actually, what you could have done, you could have just tried to use a better kernel function. Yeah, so better similarity function, if you want, because as you see, a kernel function is a kind of similarity between two items. And in support vector machines, kernels improved their power, the power of support vector machines. And like if you want to see the simplest example of a kernel is just to use the identity mapping in the feature space, like phi of x equal to x. Like actually don't map at all, like each point, each feature for x. Like x will have a number of features, and the features will remain the same. Like here, x is an array, is like x1, x2, up to, I don't know, x number of dimensions. And what we say, the identity mapping doesn't do anything. It just keeps this number of dimensions. So the input has some features, and we just keep the features that are given in the data set. And actually, what we get is a linear kernel or the dot product. Now it's the same. So the simplest kernel is a dot product. And actually, from now on, every time you see like a dot product computed between 2 points, you can just imagine that a more complex ML method or model would be by replacing this kernel, this dot product, which computes the similarity, with a more complex kernel. Because actually, more complex kernels allow us to use a dot product in a more complex feature space. Yeah. So actually, the kernel should always be formulated as a dot or inner product in a feature space. This is like the identity feature space. But from like when we use more complex kernel functions from intuition point of view, is like we want to find a feature mapping phi in a new space where solving the problem is easier. Like solving the problem is easier most of the time for us means we can solve it using a linear classifier, like a linear hyperspace, hyperplane. So maybe in the original feature space, in this feature space, we cannot find the linear separator, a good linear separator. But if we find the right feature mapping, like if we transform into a new into a new space, a more complex one, there we can find the linear separator between the classes. And the same is like for regression. We can find a better regressor model in this space. Therefore, if you want, like the kernel actually represents the similarity between two objects, and the objects are the items that you are using for your method. Like there could be text documents, they could be terms, they could be like images. And this similarity is defined as a dot product in this new vector space defined by the features. But actually what's cool is that the mapping is left implicit. Like you don't need to actually build the space and then in this new space compute the dot product, because this would be like the straightforward way. You can define your functions, like you have seen. You have like basis functions, and you can define basis functions, and then you can just compute the dot product in this new space defined by your basis functions. So a kernel is just a function which computes a dot product without actually transforming per se per se is a new vector space. And this is why we say that the mapping is not explicit. So you don't need to make explicit this mapping, like to build the features. Actually, this mapping is left implicit. It is the way the function is defined. So the function implicitly computes these features and the dot product between them, but it's not done explicitly. And actually, this is left implicit means it's not explicit. So you don't need to explicitly compute all the new features. You just need a quick way of computing the dot product of these new features. And actually, this is important because we're going to see some of these kernel functions actually have an infinite number of dimensions. And computing the dot product in an infinite dimensional space would take an infinite amount of time. So this is why they are not explicit, because sometimes you wouldn't be able to compute like an infinite number of features and then computing the dot product. But the underlying function is a very simple function which can be computed quite fast. Cool. So if you want, it's a generalization of the dot product in a implicitly feature space which is built by the kernel function. And like if you are better visually, it would be like if we have this original space with some figures, we'd like to find this feature mapping function which goes from 2 dimensions to here is 3 dimensions, let's imagine. And here in this 3-dimensional space, objects which are similar, like for example triangles, they are close together. And other objects which are similar, for example these ones, they are also close together here. Yeah, so this would be like the main idea. And everything is expressed as a dot product in this new space, but this feature mapping is not explicit, like it's only implicit in the function, in the dot product which is computed. Cool. So we are like now we have a more formal definition. It's still not like the best one. So a kernel function between 2 items x and y, it's actually a similarity measure. Is defined by an implicit mapping of some features in a space which is called like the feature space. It computes these features from the original space to the new space to the feature space, and then this function is actually a dot product in this new space. And the important thing is that this function should be expressed as a dot product in a space, in some space. This is the definition of the more formal definition of a kernel function. If we are able to show that our function is a dot product in a given space, then this is called a kernel function. And actually, if you think about it, it's a way of having more powerful features. And probably some of you know that one of the reasons the neural networks are so good is that actually they also transform the features, or they provide better features. So this is what kernels have done until we had deep neural networks. Yeah, they provided better features for our models. And actually, this similarity measure and mapping and feature mapping should include some, I don't know, invariance or a priori knowledge about the data. So this is from the ML engineer point of view. Maybe a simpler structure, like maybe we have a linear separation of the data in the feature mapping space. It would also be important, like, to know the class of functions from which the solution is taken, and maybe it could have like an infinite dimension, but still to be computationally efficient when computing the function. So we have an infinite number of features if we would have shown these features explicitly, but because this computation is only implicit, it should be efficient. Like it should, all kernel functions should be easy to compute. Like if you want, they should be maybe in theta of number of dimensions or something similar. And of course, a simple way to, so we said that we need to have like a similarity function, and a simple way to define similarity function is to take into account the distance or the difference between the inputs. So one way would be to have like what is called stationary kernels, where we have a function which takes into account the difference between the 2 arguments. And these stationary kernels, they are invariable to translations in the input space. Like if we translate both x and y with the same value, the kernel would be the same. And then we could have like homogeneous kernels, which are also called radial basis functions, which only depend on the magnitude of the distance between the arguments. So here we only take into account like the distance, let's say Euclidean distance between the 2 parameters, the 2 data points. And like it's a function. We don't care what kind of function. It could be a complex function, but this function is taking into account the distance between the 2 points. And actually, it should take into account the reverse of the distance, because we want it to be a similarity function. Like for it to be large, when the distance is small and the other way around. And so this was the first part, like what are kernels and why they are useful. The second part of the class is to show you how this dual or kernel representation arises in maximum likelihood for regression, for linear model for regression. And this is what we are doing. So we have seen, I've told you that many or almost all linear models for regression and classification can be reformulated from in this dual representation where the kernel function arises in a natural way. And in order to do this, we start from what how we computed maximum likelihood for a linear regression model. And we remember that in the maximum likelihood treatment, what we did, we wanted to minimize the error, and the error was actually the error in the data plus the error in the model. So this was like the regularized sum of squares error, and it's the difference between what we predict, like this is y of xn, our prediction, minus the correct value, the target, and it's a squared error. And we do this for all the points in the training set, and also we add a regularization norm 2 of the weights. And we want to minimize this error function, and in order to do it, what we have done, we computed the gradient with respect of j with respect to w to the weights, and we made it equal to 0. And actually, what we have found, we found how to compute the weights. And actually, this was the way how we computed the weights. This formula is not the same one from the previous class. It's different because, like, we want to express it in a way which is useful for us in the dual representation. So now the weight is actually the design matrix. So phi was the design matrix, was a matrix which had n rows and m columns. So one row for each point in the training set, and one column for each basis function that we had, like if you want for each feature that we had. And actually, the weights can be computed as the transpose of this design matrix multiplied with A, where A are is an array whose values correspond for each point in the training set, is a difference between the value of the weights multiplied with the basis functions minus the value of the target. Like if you want, is the difference between what we predict for this point, it's y of xn minus tn. Cool. And like this is one way of representing the value of W maximum likelihood. So it's phi transpose multiplied with A. And now we would like to use this formulation, the fact that W is phi transpose multiplied with A. And this is like upper phi is a design matrix. And we just replace W in the sum of squares regularized error. And when doing this, now we have this maybe clutterish way of expressing. And actually, what we have done, so here we have a binomial POW2, and we have expanded the binomial POW2. So it's W POW2 multiplied with phi POW2, and here you can see W POW2 multiplied with phi POW2. We have W POW2 gives us the fact that we have 2 times phi, 2 times phi and 2 times A. This is W POW2, and we also have phi POW2. Therefore, we have 2 times phi again. Okay, so it's a pretty nasty algebraic formulation, but this is called the dual representation. So in the dual representation, the error is not expressed in terms of W. It's expressed in terms of this A. And now we can, in order to make this formula less clutterish and simpler to write it, we define a new matrix which is called the Graham matrix. So the Graham matrix is design matrix multiplied with design matrix transpose. And actually, this Graham matrix is maybe simpler to understand than the design matrix. So actually, the gray matrix is a kernel between 2 points xn and xn. Is a kernel in which space? Can you tell me which is the space that we are using? Like, why do you say that this is a valid kernel? So the gray matrix for position n and m, it's actually the kernel between points xn and xm. Why is this a kernel function? It's a kernel function because here we have like the features that we defined using our basis functions. Yeah, so it's actually a kernel is a feature defined by the basis functions when we pick these basis functions. Yeah, so we are using the basis functions as features. I mean, these are the features that we have chosen for our representation, but we could have used any other feature. So, but in this space, it's clear that we have a dot product using the features defined by the basis functions. So actually, the gray matrix, it's a n multiplied with n matrix with kernel values, like with similarity values, if you want. The values are larger if 2 points in the training set are similar one to each other with regard to the features that to the features defined by the basis functions. And now we can express G of V in a simpler way. So it's like this A transpose K multiplied with K multiplied with A, and so on and so forth. Cool. So now we use this Gram matrix, which is full of kernel values. And now when we compute the gradient with respect of J with respect to A and make it equal to 0, we actually find the best values for A. And well, you can do this at home if you want. It's pretty simple. Like here, it's A transpose multiplied with A is the same as A power 2 from an algebraic point of view. So it's A power 2 goes in front and so on. Here we only have an A. Here we don't have any A. It goes away and so on and so forth. So it's pretty simple to express it. And what we get that A, it's actually K plus lambda multiplied with identity matrix minus 1 multiplied with T. And actually, it's a pretty similar way. W was computed in a similar way. If you remember, it was the same. It was a reverse of a matrix. It was called the pseudo inverse of a matrix, but it was of the design matrix. Cool. But actually, we are not interested in A. Like A, it's just a byproduct. Like it's an intermediate value. We are interested in the predictor function, in the regression function. So now the predictor function, y of x, or the regressor function, it's actually a W transpose multiplied with a vector of basis functions. And we remember the W transpose is actually A transpose multiplied with the design matrix, and we can express it like this. So it's actually K of x transpose multiplied with A. And K of x transposed, and like this is the important, so here appears our vector A. So it's K transpose multiplied with A. So actually, what we have reached, we reached the equivalent representation, because here K of x, it's actually an array where we have the similarity computed by the kernel functions between the new point x and all the other points in the training set. So if you want here, you can express it. It's a summation with n going from 1 to upper n out of AI multiplied with kernel of xi and x. So the value of the predictor function is computed as a linear combination. So it's a linear combination of sorry, and also here we have multiplied with tn. And here is xn. So it's a linear combination of the values of the target, and how much the linear combination is taken into account. It depends on the kernel function, like how similar the new point x is which each point in the training set. So if point x is similar with one of these points from the training set will account more. Like if you want, it's a generalized k nearest neighbor, because we don't use only k values, we use all the values, and each value is taken into account with a weight which depends with the value of the kernel. Cool. So from like in conclusion, and also from a computational point of view, so in the dual representation, we need to compute the reverse of this matrix. In the original representation, we need to compute this. This was called the pseudo inverse of the design matrix, so it's kind of similar. This was without using any regularization. If we have used regularization, it was the same here. We would have something like lambda in. So it was very similar. So we have like two possibilities. We either compute W maximum likelihood, or we compute this array of weights A. If we compute the array of weights A, now we have the dual representation where we can compute the value of a new point y of x as a linear combination of the targets that we had in the training set. And it's a linear combination using the features that we have defined, like the basis functions. But we could have used maybe better features. This would be the idea. So the prediction as a new point is given by a linear combination of the target values. But here, instead of using like the kernel function between the features that we have defined, we could have used like a better kernel. A kernel that we can pick up from existing libraries of kernels, if you want. And another conclusion would be like, in the dual representation, in order to compute A, we need to, like from a computational point of view, we need to compute the inverse of a matrix, which is n multiplied with n. In the original problem, we need to compute the inverse of a matrix, which is m multiplied with m, where m is the number of features or basis functions. And it's clear here that we have a disadvantage for the dual representation, because most of the times the number of points in the training set is much larger than the number of features that we have. So this is a disadvantage. The advantage is that the dual representation can be expressed by only using kernel functions, and we can use better kernel functions, not just the basis kernel functions that we are using. So the main conclusion of the dual representation is that we could just work with kernels without actually introducing the feature mappings and the basis function. So the introduction of the basis function was in order to have better features, but maybe we don't need to have any basis functions at all if we have very good kernel methods, which are like mathematical functions. This property we have only discussed it for like a linear model for regression. But this is also valid for linear classification models. It's also valid for the perceptron, like the precursor or the simplest neural network. And actually, a pretty studied domain in deep neural networks, if actually deep neural networks are very good kernel approximators, or even very good ways of computing kernels. So right now, the conclusion which was intended for this part of the class, and maybe this is the most important conclusion of the entire lecture, is that actually in the previous, before deep learning, one of the most important things was how to use the best kernel functions, like which was the best kernel function, the best feature mapping, if you want. And one way was for the engineer to compute by hand better features, and another way was to use a better kernel function which computes these features implicitly. And of course, a combination of the two worked best in most times. And now we use deep neural networks where we don't compute features at all. Like we give the data that we have to a neural network, and the neural network computes better features for us, like computes a better representation. Yeah, because this is what we say. Neural networks are actually computing a better representation. We don't really know what's in this representation, like they are more like black boxes and we don't know how to explain them, but the representation is clearly better because they improved tasks in computer vision, in NLP, in like time series, and in most domains, most application domains. And people try to understand why they work. And there has been a paper about 10 years ago at, maybe you know, the top conference in neural networks is called NeuRIFS, or it was called NIPS previously, but changed the name. So at NeuRIFS, about 10 years ago, it was a very good paper which paves the road if neural networks are not actually just good kernel function computations, or approximations, and it was a new paper was presented last year. The conference is in December, so I don't remember if last year or 2 years ago. And this paper is pretty good. Like if you are very big fans of deep learning, you can write me a message or an email to send you the paper in order to try to understand what happens. And from a practical point of view, I'm not really sure if anyone is listening to the class, but for a practical point of view, why would it be great to know that neural networks, deep neural networks, compute a kernel function? Any suggestions, any answers? Even if they are wrong? I'm trying to have a little discussion, to kick off a little discussion. So actually, the great thing if we would be able to show that neural networks are very good kernel computers, for example, would be that maybe at some point we can just find out which is the kernel, the underlying kernel, because it would be faster to compute the kernel per se than to to propagate and to make the inference through a very deep neural network. So from a computational point of view, if we know, if we are able to prove that that actually neural networks are kernel approximators, then the question would be, which is the actual kernel function, like which is a feature space that approximates the neural network, in order to compute this kernel explicitly. Of course, we still need to train a network in order to see which is a function, but then if we are able to find very quickly which is an underlying function, underlying kernel, then we can just compute the kernel without going through all the layers of the neural network. Yeah, it would be like a shorthand for making faster computations. Cool, and this would be great, especially like for models like transformers, which are huge models and they are not very efficient. Like transformers, even for short text, you can only run like a couple of texts per second. Cool. For longer text, it takes even more than that. Cool. So this was the second part of the class on how we compute the dual representation for a given linear model. And to show you that we can actually compute the regressor function by only using a combination of kernel functions between the new data point and all the previous ones. And now if we know this, and then we said we could just replace the dot product that we have over there with any kernel function that we had. So with any kernel that we know, maybe the kernels that we know are better feature constructors or feature mappers, if you want. And now the third part of the class is how we can build these feature mapping functions. How can we build kernels? How do we construct kernels? So we need some ways of building valid kernel functions, and of course, after building valid kernel functions, we would require not only for them to be valid, for them to be useful, like to be useful on some real-world problems. So in order to construct kernels, one way would be like to choose a feature space mapping phi of x, and then just to compute the dot product in this space. And like this is similar to what we have seen, like compute some features, like having the feature mapping, and then use a dot product in this feature mapping space, like compute the dot product in this space. And as examples, of course, we could use like polynomial basis functions like phi, the functions phi to be polynomial basis functions. They could be Gaussian. And these are the kind of kernels that we are getting. So you see, they are not the same, but they kind of look similar. For polynomial basis functions, for Gaussian basis functions, or for sigmoid basis functions, the kernels are not the same, but they are pretty similar if we are going through this phase, like using the basis functions and then transforming using the basis functions that we have computed. And now the alternative approach would be to construct valid kernel functions directly meaning without explicitly making the feature mapping. And actually, this is what we would like. So not to have the feature mapping explicitly, to have implicit feature mapping. So this is the way to do it. Like you don't want to explicitly construct the features, you want to implicitly construct them. Okay, and now we have two definitions. What is a kernel function? It should be a scalar product in some feature space, in some vector space, if you want. And the second definition is a valid kernel function is valid if we can find a definition of a mapping phi into a vector space, and then to show that the kernel can be expressed as a dot product in the space. And only to do this once when we show that the kernel is correct. So we only do it in if you want, in a mathematical or theoretical point of view to show that it's correct. And for example, let's consider, so the simplest kernel is a linear kernel. This is a linear kernel. X transpose multiplied with Z is a linear kernel. And this is called a polynomial kernel. Polynomial kernel are actually constructed from the linear kernel using a polynomial. And here we are just putting the linear kernel POW2. So this is a simple polynomial kernel function. Polynomial kernel. And of course, you could use any power. It could be POW3, POW7, and it could be any kernel function, any polynomial degree. Of course, the larger the degree, the more complex the feature space where we are computing. And now let's see what happens if we use this POW2. And we'll consider a simple example. Like we go from a two-dimensional space. So let's consider that the points that we have, x and z, they are two-dimensional. So x is z1, x1, z, x2. Therefore, z would be z1, z2. So both points, they are two-dimensional. And now let's see what we have over here. The dot product would be x1, z1 plus x2, z2, dot product, pretty simple. And then we need to compute the binomial. So it's POW2. Therefore, we have x1 POW2, z1 POW2, plus 2 times x1, z1, plus multiplied with x2, z2, plus x2 POW2, z2 POW2. And now the question is, can we express this function So this is the value the kernel is computing. Can we express it as a dot product in a given space? And the answer is yes. We can express it as a dot product in a 3-dimensional space. So it's a dot product in the feature mapping space. In the feature mapping space, now it's a 3-dimensional feature mapping space. And you can see the first feature is actually x1 pow2, z1 pow2. So actually the first axis, if you want, pow2. The second feature, or the second axis in this feature space, is actually a linear combination of the two values, of the two features, of the two original features. So it's x1, x1, x2 here, and here it's z1, z2. And we also have this term square root of 2 in order to obtain this term when we compute the dot product. And the second one is just pow2 of the second feature in the original space. So it's x2 pow2 and z2 pow2 respectively. And actually this is a feature mapping. So the feature mapping, instead of having 2 dimensions, now it goes into a 3-dimensional space, assuming that in this new 3-dimensional space, which is more complex, we could have a better separation of the data points in the training set, because we are going into the 3-dimensional space instead of separating in a 2-dimensional space where maybe the data is not linearly separable. And actually what we compute here, it's so we map in a 3-dimensional space which comprises of all second order terms of a polynomial. Yeah? So we have all second order monomials. And this is what this example kernel does. So this is a simple way of showing that a kernel is a valid kernel. So the simplest way of doing is to find out the underlying feature mapping. So this is the underlying feature mapping. We go from 2 dimensions in our example to 3 dimensions. Now the question would be, if we have like 3 dimensions, if here we have 3 dimensions, in how many dimensions do we go here? This is not so easy to compute. Maybe you can take it as an exercise. We'd go to a larger number. It's not 3, it's more. If you have the answer, you can tell me. If we start from 3 dimensions, to how many dimensions do we go?
Could be 6 because it's squared.
Yeah, it could be 6 dimensions. Actually, you see, it's all the powers of 2 if you want. So it would be for sure x1 pow 2, x2 pow 2, x3 pow 2, and then it would be a combination. It would be x1, x2, x1, x3, x2, x3. So we have 6. Yeah. We have 6. So actually, it's a number of how many second order terms you have. Yeah, second order meaning like second degree monomials. Yeah, because you see here, all of them, they are second degree. They are we have x1 pow 2, x1 pow 1, and x2 pow 1, but in total we have pow 2 and so on. Cool. So the larger number of dimensions in the original space, the larger number of dimensions in the feature mapping space. Actually, we need a simpler way to test if a function, a mathematical function, is a valid kernel without computing this explicit value of the feature mapping. From a mathematical point of view, the necessary and sufficient condition for a mathematical function which is to be a valid kernel is for it to be symmetric, and also from the gram matrix K, like the matrix that we compute between all the points, to be positive semi-definite. This can be shown using so it can be shown using if we can show that for any vector z, Z transpose multiplied with M, in our case multiplied with our matrix K multiplied with Z is greater or equal to 0. So this is like the formal mathematical definition. It's still not like very simple to do it. Like I'm sure that at least for the computer scientists and like the computer engineers and programmers, you wouldn't want to do this. And actually, a good thing is that people have already found lots of ways to construct new kernels. For example, if K1 is an existing kernel function, like if K1, K2, Ka, Kb are existing kernel functions, then we can build kernel functions by applying these methods. So this is only a simple part. There are more complex ways of constructing kernels. Like the simplest one is to put a constant in front of a positive constant in front of a valid kernel that you know. The second one is to multiply by a function f of x, which is positive f of x to the left and f of x prime to the right. Yeah, and f of x is any function. Another way would be like to use q, which q is a polynomial with non-negative coefficients. So if you have a valid kernel, then you can use a polynomial of that kernel to construct new kernel. E power kernel, so exponential power kernel, it's also a valid kernel. And then we have, like, if we have two kernel functions, we can combine them by summation or by multiplication, and they are still valid kernels. So if you knew two kernels, you can find the third one by summing them up, by multiplying them, and so on and so forth. Also, you can use like a feature mapping in order, like if you have a feature mapping, you can compute the feature mapping. Sorry. Misclick, and compute using an existing kernel. An interesting thing is that you can build similarity or kernel functions this way. So X transpose multiplied with A multiplied with X prime, where A is a symmetric positive semi-definite matrix. Like if you want here, AX as a similarity matrix, which improves. So instead of using the dot product, we transform the dot product by a feature mapping. Can you explain maybe how this works? This has also been used in neural networks, for example. And in neural networks, instead of A, you can use maybe a nonlinear transformation using a neural network. Like, how would you explain what happens here? Why is this a valid kernel? I would explain it in the following way. So we still have a dot product, but we have a dot product between A multiplied with X prime. What happens when you have A multiplied with X prime? It's actually a similar thing what happens to neural networks, because actually what is a layer in a neural network? Actually, a layer in a neural network, if you want, it's a set of weights, a fully connected layer in a neural network. It's a set of weights defined, if you want, by an A. So actually here is a feature transformation. So starting from the original features, we transform them using this matrix, and we will get some new features. And so this would be the way to think about it. So we use the original feature for the first space, but we transform the features in the second space in order to sorry, we transform the feature space for the second element in order to have a better alignment between the two features. Cool, and that was used in other papers. Maybe you'll see in other papers, without saying that this is a kernel, you'll use this. You'll see this kind of formulation in papers that you are reading. Another simple way of building kernels is like if you have X, the input, consisting of two types of inputs. For example, if it's text, is multimodal, it's text and image. You can build a kernel transformation for the first part, like for the text, plus a kernel transformation for the second part for the image, and sum them up or maybe multiplying them. So this is like, these are some ways of building new kernels if you already know one or two existing kernel functions. And actually, it's a huge domain called kernel engineering, and you can find like books, entire books with hundreds of pages, similar to Bishop or maybe a little bit smaller, which is called kernel engineering. And this was very important to know if you would work as an ML engineer about 15 years ago. Not so important right now. But like from a more visual point of view, a polynomial kernel, what it does. So this was our polynomial kernel with n equal to 2. From a two-dimensional space, we said it transforms in a three-dimensional space, and actually what it does, in this two-dimensional space, we wouldn't be able to separate with a linear classifier the triangles from the dots. Yeah, like we wouldn't have like the best separator would have been something like this, and it wouldn't have been very good. Yeah, probably this would be the best. Or I don't know, maybe you can find a better one like this. But still, there are some errors. And actually, by using the polynomial kernel, we transform it into this three-dimensional space. But it's an implicit transformation. We don't actually do the transformation. We just replace the dot product in our classifiers with the kernel, like with dot product pow2 in our case. And we'll get the points are actually separable by two-dimensional hyperplane. Like right now, you can separate the points by this two-dimensional hyperplane, which are linearly separable. And actually, this is valid even for more complex data. Maybe you would say this, the red and blue circles are for sure not linearly separable. But if you use a radial basis function kernel, with n equal to 2. This is like a Gaussian kernel, which is also called radial basis function kernel, which goes into an infinite number of dimensions. And here we have like just 4 of them. But in this infinite number of dimension space, we will be able to separate the two classes of points. Other examples of kernels, we have seen like the pow2 kernel, which only had second-order terms. If we want to have also the linear terms and constants, all we need to do is to add a plus constant to it, and then we'll go. This would be great. All monomials of order m. This is what we have already seen when it was pow2. If it's pow m, it will be all monomials of order m. Then if we have the dot product plus a constant pow m, we use all terms to degree, including m. Cool, and this is like, these are like polynomial kernels. These are all called polynomial kernels. We can also define kernels like if the two items are images, and like it would be like a weighted sum of all possible products between pixels from m pixels from the first image and m pixels from the second image, and it would be like the dot product on the values of their RGB components. I've told you about the Gaussian kernel. Gaussian kernel is usually also you can find it as a radial basis function kernel. This is an infinite dimensional kernel, one of the infinite dimensional kernels. So it's actually a radial basis function or homogeneous kernel. We said that it depends on the distance, Euclidean distance, and you see that it depends on the Euclidean distance, but it's e pow minus the distance divided by 2 sigma. And so you see, it's actually the Gaussian. It's actually the Gaussian function, no? E pow minus minus distance pow to sigma. It's a Gaussian function. So it's not a probability density, so it's not the Gaussian probability. It's just a Gaussian function similar to the basis functions that we were using. For example, to show that this is a valid kernel, you need to take into account the second and the fourth properties. The second property, so the first thing we need to do is if we write up what we have over here, so the distance x minus x prime power 2, it's actually the dot product for x minus the plus the dot product for x prime minus 2 times the dot product between x and x prime. So if you want, it's the norm of x plus the norm of x prime minus 2 times the dot product between the two. So this is the second property. So this was the second property, and now we can use. Sorry, this was the first property. The first and the second property, we can combine them. So by using the second and the first, the second was that e power. The first was that e power something. It's e power kernel. So this is a kernel. This is a valid kernel. This is a valid kernel. Therefore, the linear kernel is a valid kernel. Therefore, e power valid kernel is also a valid kernel. So this was the first property. And the second property says that if we have a function of x to the left, and then we multiply again by the same function of x prime, then we also have a valid kernel. So this is the second property. Cool. And this is why this kernel is a correct kernel formulation. Now, in order to show that it has an infinite number of dimensions, what you need to do you have any idea? Probably not. Like it's only if you have a very good mathematician among us.
Expand E as a sum, as a series.
Yeah, yes, as a series. We need to expand E as a series, but what type of series?
A polynomial, I think.
Yeah, we can use like the Taylor expansion, the Taylor series in order to expand E power the dot product, and we'll see that we would need like an infinite number of terms in order to approximate this function. So from this point of view, it's like it's a infinite number of features. So not actually an infinite number of features per se, but we cannot stop in order to approximate this function. We need an infinite number of terms. This would be the way to show it. And I've put a link, like if you want I've put a link from a kernel method lecture from Caltech by one of the most cited professors in machine learning. You can go there and look, I think it's around the 20th minute in order to see why this is true, like the mathematics behind it. And also like this Gaussian kernel can be replaced, like here we have the linear kernel, but actually we can replace it. Instead of having the linear kernel, so instead of having here the linear kernel, we can express it by any nonlinear kernel. So we could have any other nonlinear kernel function, and we can just express it like this. So e power minus 1 divided by 2 sigma, and here we have this summation. And we just replace the dot product with another kernel function. And this way you can construct an even more complex kernel function, a nonlinear Gaussian kernel. Cool. You can also define kernels from symbolic data, like a very simple kernel for sets would be like 2 power the dimension of the intersection of the two sets, and this is a correct kernel function. Like if the two sets are contain the same number of elements, the value is very large. If they don't contain any elements in common, the value is small. So this would be a very simple kernel function, but valid kernel function. When you can do the same for graphs, for strings, and for text documents. And actually in NLP, string kernels, string or text or document kernels, they are pretty good. So string kernels are pretty good, and they are even better than deep neural networks for some tasks. For example, for author identification, or for identifying the dialect identification. Like in this situation, string kernels are working better than deep neural networks. And actually, what do string kernels do? They compute they compute the n-gram overlap. N-gram overlap. So they compute, if you want, the dot product by taking into account not just n-gram. This is character n-grams. N-gram, do you know what an n-gram means? Did you discuss with Professor Traushan in the NLP lecture what an n-gram means?
Yes, we discussed today.
Okay, great, perfect. So an n-gram is actually a sequence of the n letters. It could be even spaces or punctuation. So this is how kernels work. Usually you don't remove anything from the text. So you use character n-grams, and you compute like the dot product or the overlap or the intersection or some similarity measure by using n-grams, usually going from 2, and they can go even up to 15 n-grams. And you imagine it's a pretty powerful method. So if you compute the similarity, imagine for computing the author of a text, if you find out the sum of these n-grams, you don't know which are the n-grams, but some of them, like it could be bigrams, like 2 grams are called bigrams, or it could be like 15 grams, or something in between. Some of them, they might be very good features for telling a specific author. Like you can find linguistic tics or preferences towards a specific linguistic construction. And this is why these string kernels work very good. But you actually imagine, in order to compute all the n-grams, and it's not all the n-grams of a given size, it's n-grams 2 grams and 3 grams and so on. Like in order to do it per se, it would take maybe a huge amount of memory, and it would be inefficiently to compute them explicitly. But the string kernel computes them implicitly. So it's a mathematical function, if you want, which approximates the dot product in this feature space. Cool. So we have string kernels, which are very good feature extractors, if you want, for text documents, and also for some other symbolic data. There are good kernel functions. Even for a generative model, like if we have a probability distribution, and we know like the probability of x and the probability of x prime, where the two are 2 points, we can compute a kernel by being the probability p of x multiplied with p of x prime. Yeah. And even if like the probability is conditioned by a latent variable, so you have the probability of an image given that is taken from, I don't know, a specific point, or is taken by night. This is what this latent variable means. So I would be if it's taken by night or by day, the image. Even in this situation, we can compute like a kernel by being the probability of x given y plus the probability of x prime given y multiplied with the probability of the latent variable, like the image being taken by day or by night would be, in this case, maybe the latent variable. And there you can define kernels even for Bayesian networks like hidden Markov models, and I know that you discussed about hidden Markov models at the KRR class with Professor Dina Flora. And like this was the third part of the class, and the last one, like it's a model called radial basis function network. It was a model used a lot in practice about 20 years ago. For me, it was very interesting that a student from ISI master also used it for his project without me telling him, and it got pretty good results as a baseline. So it's called radial basis function network. And we say that we'd like to build these radial basis functions where we have like the features would be the difference would be a function of the distance between x and point mu j. And it's called, so you remember radial basis function actually said it's any function which is defined by the distance. So we said that in most times this function would be an exponential function. It would be a Gaussian function. So most of the time these functions are Gaussian. In order to have a similarity function. And they can be used for exact interpolation, like if we have endpoints, to have a combination of weights multiplied with these radial basis functions. And we would have like one radial basis function for each point in the training set. But actually in ML, our data is noisy, so exact interpolation is not useful. But we would consider what happens when, not when the targets are noisy. Right now, what we do, we consider what happens if the inputs are noisy, if the features are noisy, because not only the targets can be noisy. So not only the prices of apartments are noisy, most of the time the features are noisy. The square footage is noisy because people might lie. You could say my apartment is, I don't know, has 80 square meters, but let's say it has 83 because I'm also counting, I don't know, the hallway, or let's say it has 90 because I'm also counting the balconies and so on. And other times it's just an error in introducing these features, like when you have the ad on a website, you just enter up some wrong data. So here we say the features are affected by a noise. Yeah, in our case now we have then the error. The error is a difference between what we predict and the correct target. But what we predict, it depends on the point affected by an error. So now the features are affected by an error. We are computing this error, and actually this error, it depends. We are computing the error of the regression function, if you want, the difference between the prediction and the target, and we integrate over the entire space of errors. And here, when we integrate, we use this nu of c. And actually what we get the fact, so we don't show, but we get the fact that y of xn can be expressed as a linear combination. So it's a linear combination of the targets multiplied with these functions, these radial basis functions h of x minus xn. And these radial basis functions are actually nu of x minus xn divided by a summation of all the points. So actually what happens here, it's a normalization of the basis function. So instead of just using the basis function, we normalize by dividing over the summation of the functions. Why we normalize? Because, for example, for this point, if we don't normalize, the probabilities will be small for all the three functions. So the blue one, the green one, and the red one. And after normalization, for each for the entire spectrum, from the entire domain, the summation of the normalized components will be equal to 1. So we'll have kind of the same contribution. All the time when we sum the contribution, it will be equal to 1. Cool. And these are called radial basis function networks, or the Nadaraya-Watson model. It uses normalized radial basis function. So this function nu of c, it's actually the so it's the distance between the points and between x and xn is the Euclidean distance. And actually what happens is that we can also compute the joint probability of x and t. So the joint probability of x and t, it's a function of the difference between, so this would be a two-dimensional Gaussian if you want. F would have like a difference in the features and the difference in the targets. And we can also compute which is the best predictor. And actually the best predictor would be just a linear combination given a linear combination of the targets given by some kernel functions, where the kernel functions are just normalized kernels. So if G is a kernel, you see we have a normalized kernel function. And this is called, like, this model is also called kernel regression. So if you want, you can imagine as having this Gaussian basis functions, these Gaussian kernels actually, and it's a linear combination of these Gaussian kernels. This is actually what happens if you have like 10, if you allow 10 points, 10 Gaussian radial basis functions in your model. Cool. So this was the entire lecture. For those of you who want to learn a little bit more, but this is not for the exam, if Gaussian processes are also linked to kernel methods. You have the class from Cambridge on Gaussian processes, which is pretty neat if you want to understand what a Gaussian process is. To be honest, in practice, Gaussian processes right now, they are like in real world, they are a little bit behind. So it's only if you want to understand better the mathematics. And who knows, maybe at some point Gaussian processes might catch up. But from a practical point of view, Gaussian processes are not so used. Therefore, they are not part of the lecture anymore. Cool. If you have any questions, I will be here. Otherwise, have a nice evening and see you next week. It's a class, of course, and also as a project. We're gonna share. We're gonna share a document. Actually, it will be the same document, but we're gonna add another sheet for milestone 2. So the sheet with milestone 1 you have there. We're gonna add another one for milestone 2. Cool. Until next week, please choose your SSL assignment topic. Bye-bye. Have a good evening.
Thank you. Bye-bye.
Thank you. Bye.